So we were just saying multiplying by a fraction is the same as dividing, so that's why we're getting smaller and smaller and smaller here. And that again has to do with the decimal that we're using in our function. If we use the trace feature again and move our cursor to the right, we see the behavior of y as x is increasing. So as x is approaching infinity, y is getting smaller and smaller and smaller and smaller, and it's actually approaching 0. So as x increases this time, y is approaching 0. If we move to the left along the x-axis, change our x is approaching negative infinity. As x is decreasing, we see our y's are increasing, and they will increase infinitely. So as x decreases without bound, our y is approaching infinity. Now, why would we say y is approaching infinity? Well, as we move to the left, y's are getting higher and higher. Remember, as we increase and go vertical, as we get higher up the graph, that's our y value increasing. So as the x is decreasing, the y is actually getting higher and higher and higher, approaching infinity. So let's talk about the domain and range for this decay function. In this case, again, the x's can go infinitely to negative infinity or all the way to positive infinity. So our x would be all real numbers. But again, they want us to use an inequality. So we would say x is greater than negative infinity and less than positive infinity. Ooh, it's an ugly infinity. Next, identify the y-intercept of this graph. So if I go into the table, that's the quickest way. When x is 0, y is 500. So our intercept is 0, 500. And if you go back and look at the function that they had us input into the calculator, hopefully you're starting to see some issues with this function. So right here, when x is 0, if you put a 0 into that function that they had us graph up here, anything to the power of 0 is 1, right? So we have 500 times 1. And so when x is 0, y is 500. When x is 0, y is 500. That's our y-intercept. And then that's our initial value. That's where the graph is starting. For the asymptote, what line would we be approaching? And again, we're still approaching y equals 0. We're never getting below 0 on the y-axis. So y is approaching, or the asymptote is the equation of the line that it's approaching is y equals 0. That's the x-axis, where y equals 0 is right here. We are getting closer and closer and closer, but never actually reaching 0. Okay, great. Hopefully this is all making sense. So we will move on to page 619 and then start modeling. There's just some things I want to point out right up here on page 619. This paragraph in particular is pretty important. Recall that a function of the form y equals ab to the x represents exponential growth. A has to be greater than 0 and b has to be greater than 1. A has to be greater than 0 because when a is 0, you would get 0. And that's not what's happening in our exponential functions. We don't actually hit 0. If b is replaced by something greater than 1, that common ratio plus 1, then we have an exponential growth model. So if we go back and look at the exponential growth on page 617 that they had us graph, see right here? This is what I was talking about. This in the parentheses is the 1 plus r. We are greater than 1 in what we're multiplying our a by. So in this case, b is greater than 1, so we know that this is a growth model. And in a few minutes, we'll see that when we subtract from 1, like we did on page 618, this was 1 minus r. That's why we got a value less than 1. And you can, just using basic algebra and subtraction, you can figure out what your common ratio is. All right, so back to page 619. If we have that b value that we multiplied the a by is greater than 1, then we have an exponential growth function. And here's the official rule or formula. A is the initial amount. That is important. You're going to be using that a lot. And the base, the B, right here, is the growth factor. Remember, R we called the common ratio when we were doing geometric sequences, and just another name for that is growth rate, but it's the same thing as that common ratio. Okay, you're going to see it given to you as percentages though, because we're going to be seeing real world context for these problems. And so they might say, you know, population grew by 10%. That percentage is a rate. And if you remember back to 8th grade pre-algebra, when we're doing interest and things like that, we can't actually multiply by a percentage. So what do we have to do? We have to change it to a decimal. So make sure that any percents get changed to a decimal. And then we have t. Also, t is the time interval. That's the tiny little exponent in the equation. So they are asking us to write an exponential growth function for the situation. And we're going to go through example A here and just kind of talk about it. So a painting is sold for $1,800. Sold for $1,800. So that's its initial value when it's sold. So that's the initial value. That is A. That's the starting value. Its value increases by 11%. That 11% is the growth rate. And if we change 11% to a decimal, we get 0.11. It increases by 11% each year after it's sold. Find the value of the painting in 30 years. Here's our time, that's t. So if we're writing the function, we're going to plug in all of these things that we know into this exponential growth function. So do we know A? Yes, A is 1,800. That's why they plugged in an 1,800 for A here. We have the growth factor, 1 plus R. That's what's making us grow. We're getting bigger. R is 0.11. So that's what you see here. And then T was time is 30 years. So, oh, by the way, right here, they just go ahead and combine because order of operations says that we can combine what's in those parentheses before we raise it to any exponents. Next, we're going to plug in T as 30 years. So that's what they did right here. And then we can use our handy dandy calculator and do y equals 1,800 times 1.11 to the power of 30. Okay. Now, we want to know in 30 years, how big will this be? I use the y equals screen here just so that you could see the graph. And you know what? I didn't change my window, so it may not come up nice and pretty. So let's get out of there. And we'll just plug in and see, because what you're going to be asked with these questions is to use this function, use the information they've given you from the real world problem, and actually answer the question. After 30 years, how much will it be worth? Okay, so again, 1,800 times 1.11 to the power of 30. And here we go. We get the 41,206.13 cents because it's money. Again, they've used approximation. That's what these wavy lines are because it's rounded. So after 30 years, the painting is worth approximately $41,206.13. If you were to graph it using that y equals screen, it will come out looking like this. Notice how large these numbers are. Okay, so next, if I'm asked to determine the domain and range and asymptote of this function, the domain, the x values, would have to be all real numbers that are bigger than 0. Why? Well, we can't go back in time. So time, the t time is our independent variable, as usual, and we can't have time that's less than 0. We can't go back in time. So time has to be greater than or equal to 0. When time is equal to 0, like right here, that is when the painting was sold. That's the initial amount. Next, the range, the y values of this function would be all real numbers that are greater than 1,800 because, again, we started at 1,800. That's how much it started at when it was sold. So as the years increase, the value will also increase. And if we assume that the time never ends, then the value could continue